Hello everyone. In this class we will talk about Bohr's explanation of spectral lines in case of hydrogen atom. Earlier we have discussed about the Bohr's theory, which was an improvement to the Rutherford's atomic model. There was one point where the Rutherford's atomic model was not successfully explaining why the spectral lines or discrete spectral lines of hydrogen atom were existing. So Bohr considered that according to the Rutherford, as said, the electron revolves in any possible orbit. That assumption is not correct. The electrons around the nucleus can revolve only in the specific orbits having the for which the electron possesses the angular momentum equal to n times h upon 2 pi, where n is nothing but the principal quantum number and it carries the integer values 1, 2, 3 and so on. So electron can lie only in those orbits for which the angular momentum of electron in that particular orbit it is equal to n times h upon 2 pi. So that was the correction made by the Bohr's atomic model. So now in this class we will try to understand how Bohr's this assumption and Bohr's theory of atomic model explains successfully the existence of spectral line of the hydrogen atom. So to begin with, we take the hydrogen atom. So what is an hydrogen atom? It is an atom having the one proton in the nucleus and one electron which revolves around this positively charged nucleus having only one proton. So because there is one electron which is negatively charged and a positively charged nucleus, there are two charged particles. They will have the electrostatic force of attraction between them because the charges are of opposite kind. So this electrostatic force between electron and this positively charged nucleus containing one proton, it is given by this expression 1 upon 4 pi epsilon naught into the charge on the electron multiplied by the charge on the proton, which are same, divided by r square, where r is the separation between the positively charged nucleus and the electron, or this can also be called as the radius of the orbit in which electron is revolving, because the nucleus is at the center, or we can say a very central region of the atom, and E is the charge on the electron. Okay. This force of attraction, which is the electrostatic force of attraction between electron and the positively charged nucleus, it gives rise to the centripetal force on the electron, which keeps the electron in that specific orbit. So therefore, the centripetal force, which is given by mv square upon r in general, it arises from this electrostatic force given by 1 upon 4 pi epsilon naught, or this what we have written here. From here we calculate mv square by taking r here to the other side, so it becomes on the other side this expression. Now we apply the Bohr's atomic model. Till here each and everything is same according to what Rutherford's atomic model says. Now because Bohr made some corrections, so according to Bohr, mvr means the angular momentum of electron. It will be given by n times h upon 2 pi in any specific orbit for which then n is equal to 1, 2, 3 and so on. It carries such kind of values, integer values. So from this Bohr's atomic correction regarding atomic model, we can find out V by taking m and r to the right hand side. So we get V is equal to n times h upon 2 pi m r. We call this equation to be 2. So we are using this value of velocity which comes from the Bohr's atomic model. So we have applied what Bohr's model says. So we are taking this value of V and substituting here, so that we can calculate the value of R from here. From here, when we substitute the value of V, it becomes V square here. So we have applied square, and on the right hand side everything is same. And from this equation, by transposing the terms, we are calculating here R, the radius of the orbit in which electron is lying, in which the velocity of the electron is given by this expression, equation number 2. So r from here, the radius of the orbit, it comes out to be 4 pi epsilon naught into n square h square upon 4 pi square me square, right? So everything in this equation or formula for the radius of the orbit, it is constant. 4 pi epsilon naught, it is constant. M, mass of electron, charge on electron, and H, Planck's constant. All these terms are constants. Only the thing that can change is the N, right? The order of the energy level. Whether it is N is 1 for first energy orbit, 2 for the second energy orbit, 3 for the third energy orbit, and so on. So as the N increases, the radius of the orbit also increases. So the radius is related to the value of N, means principal quantum number N, through this equation. What we understand from this expression for the radius, which is given by here, that radius is directly proportional to N square, because each and every other term is constant. Okay. So if R is given by this expression, as we have discussed here, we are substituting the value of R from here in the expression for the velocity here, right? So on substituting and making some calculation, we can also calculate the velocity. So velocity comes out to be 1 upon 4 pi epsilon naught into 2 pi e square upon nh. Again, velocity, it depends upon n only, because all other terms are constants. And velocity, it is reciprocal to the n. So from this equation for the velocity, it is clear that velocity varies inversely as the value of n, the principal quantum number n. The value of n, if it goes on increasing, that means for the orbit of higher and higher, larger and larger radius, the velocity of electron goes on decreasing, right? Okay. Now, because we have already discussed or understood what is the radius and what is the velocity of electron in any orbit according to the Bohr's quantum theory of this atomic model. Now we can calculate the energy of that electron in any specific orbit as given by the Bohr's theory. So that is actually the target we are willing to achieve, because by knowing the energy, we can easily explain what kind of radiations or what energy of radiations are emitted out during the transition in hydrogen atom. And that will explain us, or that will make us understand the existence of spectral lines existing in the hydrogen atom. So let us begin with the energy of electron. Energy of the electron in any specific orbit, it will comprise of two parts. One, the kinetic energy of electron, and two, the potential energy of the electron. The kinetic energy of electron, it is given by half mv square, because v is given by this equation, or as we have found from the Bohr's atomic model from this postulate. So we are substituting this value of kinetic energy to make it simple for this position, because we are not substituting for R here, right? So that kinetic energy, it is 1 upon 4 pi epsilon naught into E square upon 2R, as comes from here. We are substituting value of V from here and making some calculation, and it appears as this. Alternately, we can also make use of this formula here. So half, we can multiply it by half on the left hand side and on the right hand side. So from there also we can easily calculate the kinetic energy. So this kinetic energy of electron in any orbit comes out to be 1 by 4 pi epsilon naught into E square upon 2R from this equation, right? And similarly, in the same orbit, what is the potential energy of the electron? It is given by the interaction between the electron and the positively charged nucleus. So it will be given by 1 upon 4 pi epsilon naught into minus E, the charge on electron, into plus E, the charge on the nucleus, divided by R, the separation between the two, which is nothing but the radius again. So it is same radius as we have used for the kinetic energy. And from there, we calculate the potential energy to be 1 upon 4 pi epsilon naught into, it becomes E square upon R. Minus sign we are writing here. So this is the kinetic energy and second equation is the potential energy. So total energy will be sum of the two. So total energy we can write it to be En, which will be sum of the kinetic energy and the potential energy. So when we add these two and make some mathematical calculations, we get this expression for the total energy of the electron in any orbit having radius r. So this is given by minus 1 upon 4 pi epsilon naught into E square upon 2r. So we have to remember this expression in general. Now we can substitute the value of r so as we can express the energy of any orbit in terms of its principal quantum number. So for substituting the value of r from here, again this is the value of r, we are substituting the value of r in this equation here and making some calculations. So the energy of any orbit or any nth orbit in which electron is revolving, so it will be given by minus square of 1 by 4 pi epsilon naught times 2 pi square m e to the power 4 divided by n square h square. Again from this equation we can understand that all terms are constants except value of n. So that means energy of an electron in any nth orbit, it will be inversely proportional to the square of that orbit, number of that principal quantum number for that orbit. So this is the overall expression we have to keep in mind. So what we have just did, we have just started from the electrostatic force of attraction between electron and the positive charged nucleus of an hydrogen atom. This electrostatic force is the reason for the, or we can say this electrostatic force gives the centripetal force to the on the electron. So from here we have just written mv square, which comes out to be this, and then we have applied Bohr's model, and from there we found the value of velocity which we substituted here and calculated the radius. So this is an important expression. Okay, so after finding the radius we found the velocity, and on finding the velocity we have calculated the total energy by knowing the kinetic energy and potential energy of the electron in any specific orbit, and this is the final expression for the energy. So this is the equation which we will take now onwards for discussing the for answering the existence of spectral lines in case of hydrogen atom. So to begin with, we just write the energy of an electron in any nth orbit as this, as we have found here. In the first hand, we will calculate the energy of each and every orbit, for example. So for the very first orbit, n is equal to 1. So we are substituting n is equal to 1 here, and all other terms are already constants, which we can write or substitute directly. So for n is equal to 1, this is the only term which is changing, n square here. So it will be 1. So we are getting only this term on the right hand side. On substituting all the constants and making some calculation, the energy comes out to be minus 13.6 electron volt. This is the energy of the very first orbit of the hydrogen atom. In this energy orbit, the electron can lie with this amount of energy. Similarly, for n is equal to 2, now there will be no energy orbit between n is equal to 1 and n is equal to 2. After this energy level or energy orbit, there can be only the orbit for which n is equal to 2, and the energy will be calculated according to this to be this. So E2, we are substituting n to be 2 here. So it will be 4. 2 square is 4. So that means all other terms are similar to the in the first case, means the energy in the first energy orbit, energy of the first orbit. So we can write this term to be E1 divided by 4, because this is the only term which is differing. So this will be equal to E1 is nothing but minus 13.6. So therefore this energy of the second orbit, it will be E2 minus 13.6 divided by 4 electron volts. You can make this calculation to write the energy for the second energy orbit. There will be no energy level in between n is equal to 2 and n is equal to 1. So either the electron can lie in n is equal to 1 energy level corresponding to this energy, or electron can lie in the orbit having n is equal to 2, the principal quantum number 2, so that its energy is this. Similarly, for n is equal to 3, the next energy level will be only n is equal to 3 in case of hydrogen atom, right? So, for n is equal to 3, the energy comes out to be, by substituting n is equal to 3, it becomes 3 square here. So, therefore, 3 square is nothing but 9, and all other terms are same as in the first expression. So, this we can also write as E1 upon 9 simply. So, for substituting value of E1, it is minus 13.6 as here divided by 9 electron volt. Calculation can be made. Similarly, for n is equal to 4 and 5 and 6 and so on. And similarly, for n is equal to infinity, because this energy goes on changing, right? And it is going to become more and more positive. This is most negative energy. This is comparatively less negative, means higher energy level. This is even higher energy level. So for the energy level for which the value of n, the principal quantum number, is infinity, which is lying very far off from the nucleus, the energy of that will be 0. Here 0 means the highest energy level, right? So this is called as the energy quantization, because the electron can lie only in the orbits in which its energy is given by either this or this or this. So this is called as the energy quantization. Similarly, just like charge quantization, right? Okay. This energy of different energy levels or orbits can be shown in terms of this diagram. This is the diagram of energy levels of hydrogen atom. For n is equal to 1, this is the lowermost or closest to the nucleus energy level. Its energy is given by this 13.59 or approximately 13.6. And for n is equal to 2, it is already calculated to be minus 13.6 divided by 4 electron volt, and it comes out to be 3.4, minus 3.4. So it is becoming less negative, means this energy is higher than the earlier one, for which n is equal to 1. And for n is equal to 3, we have calculated the energy to be minus 13.6 divided by 9. So on calculation, finding the ratio, we will find the energy to be 1.51 and minus 1.51. And similarly, for n is equal to 4, 5, and for n is equal to infinity, the energy corresponding to that, it will be 0. This is the highermost energy level in case of hydrogen atom. So electron in hydrogen atom can take only any one of these energy orbit and no other orbit, right? Now we are approaching towards the spectral line of hydrogen atom. How does they exist? So we have calculated the energy of each and every possible energy orbit which can exist according to Bohr's theory. Okay. So this is the energy spectrum of hydrogen atom. So transition takes place only when electron jumps from one orbit to other orbit, means the orbits of different energy levels. For example, when transition takes place from higher energy orbit E2 to energy orbit E1, E2 is given by minus 3.4 electron volt and E1 is given by minus 13.6 electron volt. In terms of diagram, we can just indicate it just like this to make it more easy to understand. This is the lowermost energy level for which n is equal to 1, and the energy corresponding to this is minus 13.6 electron volt. You can write here, right? So when transitions takes place from any higher energy orbit to this energy orbit, the radiation, or we can say energy, will be released, because the electron can come to the lower energy level only by releasing the energy, and electron can have the energy only given by the Bohr's atomic model corresponding to the particular orbit. For example, if electron is lying in an energy orbit for which n is equal to 1, then it can have energy only equal to minus 13.6 electron volt. It cannot have any other energy. So if transition is taking place from energy orbit n is equal to 2 to energy orbit n is equal to 1, then some energy will be released because this energy level is high. In this energy orbit, the electron is having the higher energy. So what is the difference between the two energy levels? Equivalent amount of the energy will be released by the electron or emitted by the electron. Only then it can take this lower energy level. So this happens always. So whenever transition takes place from higher energy orbit to low energy orbit, energy will be released. And whenever transition of electron takes place from low energy orbit to higher energy orbit, the energy that can happen only when some energy is given to the electron or electron takes the energy. Right? Okay. So how much energy electron releases or absorbs during the transition? It depends upon the energy levels between which the transition is taking place. So to make it clear, I'm writing these two equations for the energy levels. EI, the initial energy level in which electron was earlier lying, and the final energy level EF in which the electron is finally coming after transition. So this is the same general expression. Only the thing which is changing is principal quantum number, and here it is NF, right? So energy will be released in transition from initial energy level to final energy level. So that energy released, it will be equal to the difference of the energies of the two energy levels in which the transition is taking place, between which the transition is taking place. So energy released, it is given by EI, the initial energy level, minus EF, the final energy level. So this energy released, according to the expression, it is written as h nu. The radiation will have the energy which will be given by h nu. So this energy is given by h nu is equal to EI minus EF. Now nu is written as C upon lambda, right? And from there we are calculating the expression for the lambda. So the formula for the lambda means wavelength of the radiation or energy which is released. It will be given by EI minus EF upon HC. So when we substitute these values of energy of the initial orbit and energy of the final orbit from these two expressions and make some calculation, we get the formula for the wavelength of the energy that will be released during the transition in case of hydrogen atom. Right? So here each and every term except this term in the bracket, this term, it is nothing but the constant, and this constant, it is called as Rydberg's constant, which we represent as RH. So RH is given by square of 1 upon 4 pi epsilon naught into 2 pi square me square upon ch cube. So this is Rydberg constant. So if we substitute all these constants here and make calculation, the value of Rydberg's constant comes out to be 1.09678 approximately into 10 to the power 7 per meter. So in place of this, we are substituting its value, which we indicate it by RH. So therefore this expression turns out to be 1 upon lambda is equal to RH into, inside the bracket we are left with only 1 upon NF square minus 1 upon Ni square. So the wavelength of the energy emitted out, it will depend upon the energy orbits in which the transition is taking place, Ni and Nf. So what we just did, we just write the expressions for the initial energy of the initial orbit and energy of the final orbit. Initial orbit is the one in which the electron was earlier lying, and final orbit is the one in which electron finally coming after transition. So the energy will be released equal to the difference of these two energy levels. So total energy released, it will be given by the difference of the two energy levels. So energy which is released, it can be written as h nu, and nu can be written as C upon lambda. So therefore from here we get the expression for the wavelength of the energy which is released or radiation which is released during the transition of electron in case of hydrogen atom. On substituting these values of EI and EF from these two equations, we can get this formula. So what we see here is that this is something which is common and is constant. So this constant, it is called as Rydberg's constant, and its value on substituting these all constants is calculated to be 1.09678 into 10 to the power 7 per meter. So in place of this lengthy expression, we can simply write RH. So therefore the wavelength of emitted energy radiation, it will be 1 upon lambda is equal to RH times this term inside the bracket. Okay, now we can talk about the different energy radiations emitted in case of transition of electron in hydrogen atom by using this formula. Okay, so this is the formula of the wavelength of the energy which is released or radiation which is released. So if the transition, I want you to focus at this diagram again. So if the transition is taking place to the energy level, lowermost energy level, for which n is equal to 1 from any higher energy orbits, right? The equation to calculate the wavelength of the radiation which will be released, it will be written as just this. Here the final energy level is 1 for which n is equal to 1, right? Because transitions are taking place to the energy level for which n is equal to 1. So final energy level is NF is equal to 1. So that's why in place of NF we are writing here 1. So it is 1 square here minus 1 upon Ni square. There may be any higher energy orbit from which the transition are taking place. It may be second energy level, third energy level, fourth energy level, and so on. So the wavelength of the radiation that will be which will be emitted out in this case, it will be written as this. So when we find the wavelength for example second energy orbit to first orbit released in second energy orbit to first energy orbit, the wavelength calculation of the wavelength comes out to be such that it falls in the visible region, or sorry, ultraviolet region, not visible but ultraviolet region. So all these energy radiations emitted out from second energy level to first, third to first, fourth to first, all these are together are called as Lyman series. So these are called as the Lyman series. All these radiations are called to be lying in the Lyman series. Similarly, if the transitions are taking place to second energy level for which n is equal to 2, right? For which n is equal to 2. Again, let us focus on this diagram. Now the transition are taking place to the energy orbit n is equal to from any higher energy orbits. So higher energy orbits will have n is equal to 3, 4, 5, 6, 7 and so on. So when transitions are taking place from any higher energy orbit to the energy orbit for n is equal to 2, then the wavelength will be written as this. So now the final energy level here NF, the final energy level NF is 2. So therefore in place of NF we are writing 2 here. So it is 2 square minus 1 upon Ni square, when Ni is any higher energy orbit. So it can have values 3, 4, 5 and so on, right? So the energy will be released for which the wavelength can be calculated by this formula. So when we calculate all these wavelengths, we see that they will fall in the visible region. And these series of radiations are called as the Balmer series. Similarly, when transitions are taking place to n is equal to 3, right, from any higher energy orbit for which n is equal to 4, 5, 6 or so, the wavelength can be calculated by this by putting NF, because transitions are taking place to the final energy level for which n is equal to 3. So it is 3 square here from any higher energy orbit for which n can be 4, 5, 6 or so. So we see that the wavelengths are such that they fall in the infrared region. And all these radiations are emitted out. They are called as the radiations of Paschen series. Similarly, when transition takes place to energy orbit for which n is equal to 4 from any higher energy orbit for which n is equal to 5, 6 or 7. The wavelength can be calculated by putting the value of nf, the final energy level, to be 4. So it is 4 square here. On calculation, we can see that all these wavelengths are similar to the infrared region. These radiations also exist in the infrared region. And all these radiations emitted out, they are together called as the bracket series, radiations of the bracket series. And lastly, when transitions takes place to the energy orbit for which n is equal to 5 from any higher energy orbit 6, 7, 8 or so, the wavelength can be calculated by putting nf to be 5. So it is 5 square here. And ni can be 6, 7 or so. Okay, so we see that the wavelengths are so that they fall in the far infrared region. And all these transitions in this case are called as the radiations of Pfund series. So these are the different kinds of radiations which are emitted out in case of hydrogen atom. So these are the spectral lines, the we can say discrete or quantized lines in case of hydrogen atoms. Lines means the radiations. Lines means radiations. You can have this diagram here again. So transition to n is equal to 1 are taking place from all higher energy orbits. N is equal to 2, 3, 4, 5 and 6 shown by these orange colors. So these are called as the radiations of the Lyman series, and they will fall in the ultraviolet region. Similarly, when transitions are taking place from any higher energy orbit to an energy orbit for which n is equal to 2, the radiations are called as Balmer series, and radiation are transition taking place to n is equal to 3 from any higher energy orbit, they are called as Paschen series, and transition taking place to n is equal to 4 from any higher energy orbit, they are called as the bracket series. And lastly, transition taking place to the energy level n is equal to 5 from any higher energy orbits 6, 7, 8 or so, they fall in the far infrared region, and together they are called as the radiations of Pfund series. So this is how the Bohr's theory now successfully explains the existence of spectral lines, the discrete energy radiations emitted out in case of hydrogen atom. So therefore, it was the Bohr who successfully explained the hydrogen atom. And this Bohr model also explains all other light nuclei just like lithium and so. So that is all about this class. Thank you.